So the last topic for this week is how we can evaluate discriminant functions and our classification rules. So one simple effect size for evaluating a binary classification is Cohens kappa. And you've probably seen Cohens kappa in other places. It's used in a lot of different domains that involve types of classifications or checking the agreement between raters and stuff like that. So in the case of classification, we can call P0 the proportion of correct classifications, and PE is the proportion of correct classifications one would expect by chance alone. So this is looking at how many extra correct classifications you get rather than chance alone. So here is how we can estimate it based on the terminology we've been using. So P0 is the number of true positives plus true negatives divided by the sample size, while PE is the proportion of healthy classifications and sick classifications divided by the sample times the number of sick classifications, both divided by the sample size, plus the number of, the number of actual healthy and number of actual sick multiplied by each other divided by the sample size, and the number of positive classifications divided by the sample size times the number of negative classifications divided by the sample size. So we can easily get these from our data using the contingency table. So we get P0 as the sum of the diagonal elements of the contingency table. So we see those are our correct classifications. So I can just take the sum of the diagonal and divide by n. And so that's 0.825. And so for PE, we can use the marginal proportions for the columns and the rows. So we rewrite the original PE as the sum of row 1 divided by n times the sum of row 2 divided by n, plus the sum of column 1 divided by n times the sum of column 2 divided by n. And that gives us the PE. And then we just plug into our kappa ratio, P0 minus PE divided by 1 minus PE. And so that's our Cohens kappa, which ranges from -1 to 1, and any values above 0 represent better than chance classification. So higher values are better. Of course, you can get kappa with the Cohen kappa function from the psych package. So here the estimate column for unweighted kappa is what matches what we had originally. So you can also enter the original data and classification instead of the contingency table. So here I just entered the contingency table itself. And here I put in the actual data of the actual true classifications and the predicted classifications. So kappa is a general measure of the quality of classification across all error types. Sensitivity and specificity are types of effect sizes for the two types of errors that can be made separately. So false negatives and false positives. Sensitivity, which is essentially the true positive rate, is the number of true positives divided by the number of true positives plus false negatives. So people who are classified as people who are actually positive but classified as negative. So the denominator here is the total number of actual positives, so actual sick people. So it's the proportion of sick of actual sick to correctly classified actual sick to all total actually sick. And then specificity, which can be considered the true negative rate, is just the opposite. It's the number of true negatives divided by the number of true negatives plus false positives. So it's the correctly classified negatives divided by the total negatives. So once again, for reference, here's our contingency table. We can compute sensitivity and specificity pretty easily using these values. So sensitivity here is just 84 divided by 84 plus 16. So this is my true negative. Sorry, this is specificity, right? I think I have this backwards. Oh no, this, right, sick is positive. So true positives divided by true positives plus false negatives. So this is false negatives are sick people who are classified as healthy. So that's my sensitivity, 84 divided by 84 plus 16, and then specificity is just the reverse. So it's the other elements So the caret package has sensitivity and specificity functions, which you can get quite easily. Both require you to enter the predicted values first, then the actual classification as each is factors. So first you enter the estimated classifications by the discriminant function, and then the actual true classifications. So for sensitivity, that you then must specify the value corresponding to a positive classification, and for specificity, the same for a negative. So it's a little bit of a funky function, or they are a little bit funky. So you remember to enter everything as factors. And then for sensitivity, I define positive as sick, and then specificity, I define negative as healthy. And these values obviously match what we got before. So kappa, sensitivity, and specificity help evaluate a particular classification. So these are ways of evaluating the classification. To evaluate a full discriminant function, we could treat its output as a probability rather than as a binary classification. So in addition to class, the predict function also gives us a posterior probability. So this evaluates the discriminant function and then converts the return quantiles to their corresponding probability values. And it looks like the version R uses has some kind of minor sample size correction, because it was slightly different from what I got when I did this by hand, but it was very close. It was just a little bit off, enough that it wasn't just a rounding thing, but it looks like there's some kind of correction that biases it a little bit towards uniform distribution. So here we can see all of the output elements from the predict function. So here I'm just saving the output of predict as PR, and then I'm just looking at the class, posterior, and this X, which give us the class is the classification that we've seen. The posterior are these two sets of probabilities, so the probability for healthy and the probability for sick. And then X, which is just showing up as LD here, these are the evaluations of the discriminant function. And these are what can get converted into these probabilities. A receiver operating characteristic curve is a way of graphically assessing a discriminant function by varying the classification criteria. So what it does is it plots specificity against sensitivity using different probability thresholds for classification, so you can see how the two different types of error rates trade off against one another. So one way to interpret the ROC curve is that it tells you what sensitivity and specificity might be under different base rates or priors and or different cost functions. So the PROC package can give us an ROC curve for us. So what we need is the probability in this case from the predict function, along with the correct classification. And then we use the ROC function to create an ROC object, and then we can plot the ROC object. And I've included a few extra non-default arguments to make the plot a little bit nicer here. So here I load up the package. I get my probability. So I only want the probability of positive here. So I just take the second element of the posterior with the second column. So these are the probabilities that the classification should be positive, P6. So then I fit my ROC object using the actual class and the predicted probability. And then I plot it. And so this is our ROC curve. And so we can see on the x-axis, we have specificity decreasing from 1 to 0. And then on the y-axis, we have sensitivity increasing from 0 to 1. So this is what this is showing is how as you increase specificity, or how as specificity decreases, sensitivity increases. So essentially, really what we're saying here is if we have perfect specificity, which means the only way to, well, not the only way, but if we go all the way into the extreme and say, I want my specificity to be perfect, I want to classify every, if I want to classify, sorry, that's on the left side, I want to classify everything as a negative, then I'm going to make zero true negative, I'm going to make zero errors. Every negative is going to be a true negative. And so my sensitivity is going to thus be 0 because all of my positives are going to be classified as negatives. So what we're looking for here really is that there's minimal trade-off, so that when we have relatively high specificity, we also want to have relatively high sensitivity, and we want to see if there's any maybe patterns where we have much higher sensitivity than specificity in certain regions. But either way, what this helps us see is how the two types of errors trade off against one another. And so that's sort of being explained here. So what we're really, the sort of key interpretation from an ROC curve is that we can interpret this area that's under the curve. So the more area that's under the curve, the less sensitivity and specificity trade off against one another, and the better our discrimination is doing, regardless of our classification criteria. So if we have a lot of area under the curve, it's sort of saying it doesn't really matter what our actual classification criteria is. The discriminant function is still doing a really good job of separating our two classes. And so we can calculate the area under the curve as a proportion with the AUC function. So in this case, it's 88 or it's 0.88. And the diagonal line, we can print this on the plot. And so if we call print AUC equals true, and so we also want to use the diagonal line as a reference. So if our classification was not working well and was essentially just randomly guessing, that's where we would expect to see the curve be. We would expect it to sort of line up along this diagonal line. That would be equivalent to our classifier just randomly guessing. And if it's somehow below that line, it means that our classification is doing worse than chance would be expected to do at that point. So what we've done so far is evaluate our discriminant function by looking how it classifies the data on which it was fit. This has a problem. So what is that problem? So of course, our classification is going to work well in the data on which it was based. So we're looking at we're fitting a model, and then we're checking the model on the data itself. And this is similar to the idea that R squared is upwardly biased. We know that this model is going to be optimized for the data on which it was fit, but what we really want to know is how well it performs on data on which it wasn't fit. So if you have multiple data sets, one way to evaluate a discriminant function is to test the version based on each data set against one another. So this is called cross-validation. So here we can now use the second simulated data set, the unbalanced data set, to cross-validate our model. So we can take the discriminant function and apply it to this new data set. So to do this, I can use the predict function and specify new data. So the new data argument says that I want to use my discriminant function, but I want to use it on some new data. And so that will generate predicted values for the new data. The one thing I have to be careful about here is that, remember, the prior from my original data set was based on that data. So the prior for the first discriminant function that I fit is going to be 0.5 and 0.5. So we know that this doesn't match the distribution of the new data. So we know that the proportion in this new data is 0.9 and 0.1. But the predict function is assuming that you don't know. The predict function is going to assume that you don't know anything about the correct classification in the new data. It's not taking that into account. It's just taking your function, looking at the new data, the discriminants in the new data. So it's just looking at temperature and oxygen in the new data and trying to predict the classification. It's ignoring what the correct classification is, assuming you don't know it. So it's inheriting the prior used before. So you can and should, in this case, specify a new prior with the predict function. So here, when I do the prediction in my cross-validation, I'm going to specify the prior as being the correct prior, so 0.9 and 0.1. And so here's a contingency table for my classification based on this model. But we can also do all the stuff we've already done. So we can plot the classification, we can look at kappa, look at sensitivity and specificity, and then analyze the receiver operating characteristic curve to assess the discriminant function. And so here's the plot. So this is the unbalanced data, but it's using the function, the discriminant function, the model, based on the balanced data. But I just adjusted the prior, so it's correct. You can see it's doing a pretty good job, as we saw in the contingency table. So we can check Cohen's kappa. So we get a somewhat lower kappa here, but still pretty good, 0.49. So that's still quite a bit better than by chance alone. So sensitivity and specificity. So specificity is really high. So our true negative rate is very high, but our sensitivity is kind of moderate. Our true positive rate is pretty low. And that's partly probably just a function of the fact that there's so few actual positives in the data. And here's our ROC. So we see that we have a quite a bit of area under the curve. So we have very little area outside of the curve. The area under the curve is 0.92, which again tells us that there's not much trade-off between sensitivity and specificity. That they're both going to be pretty high no matter where you land. Although in the because of the way our prior was set up, we wound up our classification wound up with specificity being really high down here, which by almost necessitates that sensitivity is going to be a little bit low, because we have such high specificity that sensitivity can only be so high. But if we wanted to, we could relax our requirement on specificity a little bit, and that would increase sensitivity quite a bit, although we'd be making more total errors if we wound up like here on the ROC curve, for example. But we would still be doing a pretty good job of classification. So our discriminant function performed pretty well, and so there are some other considerations for doing cross-validation. We might want to adjust our prior with a cost function. I'm not going to go through that here, but that's something we could think about. We could also cross-validate in the other direction. So I could fit the model on the unbalanced data and then validate it on the balanced data. A lot of times when you do cross-validation, you'll go in both directions like that. I'm going to skip that here for time, but that's something that you could certainly do. So the last thing that we could do is consider a case where we don't have two data sets, which is going to often be the case. We're usually only going to have one data set. So one solution is to split the data in half and cross-validate, but that wastes a lot of statistical power because you're fitting the model just based on half the data. So one technique for the solution is known as leave one out cross-validation. So the idea behind leave one out cross-validation is you're going one at a time, eliminating one data point at a time, fitting the model on the other n-1 data points, and then predicting that last data point, and then seeing how well each data point is predicted based on the function from the other n-1 data points. So the LDA function has a built-in argument for this called CV. So when you set CV equals true, it does something a little bit different. So instead of doing the discriminant function, it does the leave one out cross-validation. So now when you set CV equals true, the actual LDA object is a little bit different. It's a little bit more like the predict object. So it has the classification based on the leave one out cross-validation, and the posterior probability based on the leave one out cross-validation. And so again, we can do all the same things now. So I'm going to check the contingency table. So we see in this case, this is based on the leave one out cross-validation. We do almost exactly as well as we did in the case where we check the data based on the full data set. So we made one extra false negative error. So we see we had one extra healthy person was classified as sick as compared to the original contingency table. So pretty similar result. And so all the other results are going to be pretty similar. So here I'm plotting the cross validation as I did before. So here I'm checking kappa. So kappa is 0.64, very similar to what we had, just slightly lower. And so sensitivity is 0.84, specificity is 0.8. So again, basically the same. And the AUC on the ROC curve is slightly lower because we made that one extra error, but it's still very similar. So we still have a pretty good trade-off between sensitivity and specificity. So a lot of area under the curve, which is good. And so leave one out cross-validation is really a much better way of assessing both a discriminating function and a classification. Unlike the cross-validation between data sets is fine to do, especially if you have just naturally two different data sets for some reason and you want to cross-validate on them. But leave one out cross-validation is a much more valid way of assessing a discriminating function if you only have one data set. And these methods don't only work for discriminant analysis, but pretty much any kind of classification analysis, which could include, again, logistic regression or probit regression or something like that. We just looked at them in the context of discriminant analysis here because that's what we're learning.